All right, let's get right into it. Today, we're talking about a brand new scientific paper that does something, well, a little unusual. See, instead of just proposing a neat idea, it throws down a gauntlet, a direct challenge to experimental physicists everywhere, basically daring them to prove its wild predictions right or wrong.
You know, every huge leap in physics starts with a powerful idea. Way back in 1889, the legendary physicist Heinrich Hertz said, "We have to imagine." He was a master of both theory and experiment, and he knew that imagination is what pushes us from asking what if to discovering what is. And honestly, the paper we're digging into today is just dripping with that kind of bold, scientific imagination.
So, where is all this happening? Well, we're diving headfirst into a new quantum frontier. And this is a super exciting place to be. It's this intersection where you have quantum sensors, exotic materials with bizarre properties, and our amazing ability to control light all starting to collide. And it's in a collision like that where the really new, game-changing stuff happens.
Now, this whole scientific drama is playing out in a notoriously difficult space called the terahertz gap. You can think of it as the last real frontier of the electromagnetic spectrum. It's this slice of frequencies that has incredible promise for things like 6G or even more advanced sensing technology, but it's just incredibly hard to work with. For decades, it's been a massive headache because these waves are in a weird spot, too fast for normal electronics, but too slow for typical lasers and optics. And that's the big problem this whole story is trying to solve.
Okay, so to really get a handle on the challenge that's being laid down here, we need to meet the two main characters in this scientific story. On one side, we've got a very special kind of diamond, and on the other, we have a true wonder material of modern physics.
So player number one is something called a diamond nitrogen vacancy center, or just an NV center. The best way to picture this is as a tiny, perfect little quantum compass that's embedded right inside the diamond's crystal structure. It's basically a deliberate flaw, an imperfection that happens to be an unbelievably sensitive detector for the absolute tiniest magnetic and electric fields.
And our second player? Well, it's found in graphene. You know that famous sheet of carbon that's only one atom thick? In graphene, you can get all the electrons to move together in these synchronized wave-like patterns. They're called plasmons, and you can almost picture them as little ripples of electricity. What's so cool about them is that they can grab onto light and squeeze its energy down into these tiny, incredibly intense fields, way, way smaller than the wavelength of the light itself.
So here's where it gets really interesting. This new paper is all about smashing these two worlds together. The whole idea is to combine the quantum sensing superpower of that diamond NV center with the light-squeezing ability of the graphene plasmons. The goal? To create a device that's way more powerful than either of its parts alone.
And this gives you a perfect picture of the concept. So you start with your NV center sensor that's inside the diamond. Then you put a layer of graphene just nanometers above it, but here's the trick. It's not just any old sheet of graphene, it's patterned into a fractal shape, which makes it act like a hyper-efficient antenna. This whole setup creates this tiny little cavity that traps and massively amplifies those tricky terahertz waves, focusing all that energy right onto the quantum sensor.
And this brings us right to the heart of the story. This research paper is not just some gentle suggestion for future work. No, it is a scientific gauntlet. It is a list of demands, a direct challenge thrown down to experimental labs all over the world. And it basically says, here is our theory. We dare you to prove it wrong.
The authors don't hide behind vague ideas either. They lay out 6 specific, measurable, and, this is the most important part, falsifiable predictions. Now in science, falsifiable is the absolute gold standard. It means your idea can be tested in the real world, and if it's wrong, an experiment can prove it's wrong. No wiggle room. And here it is, the gauntlet itself. This is basically the checklist for any lab that wants to take them on. First, they say, prove the extreme light confinement in that fractal structure. Next, they predict a specific boost to the quantum vacuum field and a measurable change in how the diamond emits light, which is something called the Purcell effect. They even dare people to measure tiny changes to quantum-level forces. Each one is a distinct, measurable effect. And maybe the biggest part of the challenge is that last point. They claim all 6 of these are testable with technology that's already sitting in labs today.
Now, this whole public challenge thing might seem a little, aggressive, but honestly, this back and forth between bold theories and tough, real-world experiments is the fundamental engine that drives all of science forward. It's how we figure out which brilliant ideas are actually right.
It really helps to think of it like a conversation. On one side, you've got the theorists.
They build these beautiful models and ask, hey, what if the universe works like this? And on the other side, you've got the experimentalists. They're the ones who get their hands dirty, build the machines, and ask, okay, that's a cool idea, but is it true? You just can't have one without the other.
And don't get me wrong, this isn't just pure science fiction. While this specific device they're proposing is still just a theory, we are already seeing some really powerful hints from real-world labs that this whole approach is absolutely on the right track.
I mean, check this out. A recent experiment that used a pretty similar graphene setup actually achieved an incredible 9% amplification of THZ waves. Now that means they literally got more energy out than they put in. They built a real amplifier. Just proving that this kind of gain is even possible, especially at room temperature, is a huge deal. It's a massive proof of concept.
So here's the crucial point. The authors of the paper wrap it all up with a direct call to action, which you can see right here. They're not just publishing their theory and walking away. They are spelling it out, providing the recipe and the exact benchmarks for success. They're basically telling the world, go build it. Here's exactly how you'll know if you got it right.
And that leaves us with this final, really provocative thought. A truly bold theory is on the table. The tools to build it and to test it are available, right now. The future of this technology, and maybe a whole revolution in science, is just sitting there, waiting for an answer from a lab somewhere. So the only question left is, who's going to be the first to pick up the gauntlet?